Welcome to the second lecture on statistics for the course Research Methods 1. This lecture is a continuation of what we talked about already, and it should tie in with the lab sessions that are also organized in this course. And today I'd like to talk to you about a couple of things. First, we'll do a quick review of what has been discussed already, and we'll build on this. Then we'll expand our understanding on associations between two variables. That's a complex way of saying, let's see what alternatives we have for Pearson's R that we have discussed already. After that, we'll expand on regression analysis that we've also discussed, and we'll introduce multiple regression analysis where we work with more than just two variables. And finally, we have some quality control checks that we should discuss before we throw you in the deep and you can do your own thing with statistics. So first of all, it's important that we discuss the significance level. I did talk about this in my previous lecture and gave the example of life expectancy rising in the Netherlands and how we might check that as a hypothesis against real data. And essentially what we looked at was the likelihood of us finding a certain result based on random chance alone. And you see that represented in this normal curve here, where the observations that are in the tail ends of this graph would be the least likely observations, where the more likely observations are in the middle. So this is the center of the distribution, and we talked about the mean, the median, and the mode that would describe that, and we talked about standard deviations that can describe how far away a certain observation might be from that center, as well as saying something about how spread out a certain distribution is. For the likelihoods that we find a certain result based on random chance alone, we use the p-value, as it is called. And in the lecture that you watched earlier about statistics, we compared the p-value that is calculated, in our case by the program SPSS that you're being introduced to, and the alpha value that we can set as researchers. And then we compare the two. We say if the p-value is indeed smaller than the alpha value, then we say that that is statistically significant. Statistical significance can be expressed in different measures of precision, so to speak. So how unsure are we willing to be? And here are some common examples where with a p-value of 0.1, a p-value of 0.05, 0.01, and these correspond to alpha values of respectively 10, 5, and 1%. In other words, we are with a p-value of p equals 0.01, we are 1% unsure about rejecting the null hypothesis. All right, so there's a 1% chance of it being random chance that we find this result. So again, when we test hypotheses, we compare the p-value to the alpha value. If p is smaller than or equal to alpha, then we reject the null hypothesis and we accept, in parentheses, the alternative or research hypothesis. It says accept, but technically speaking, we only show that it is unlikely that this is random chance. We never really have definitive proof that any hypothesis is true, including the null hypothesis, as a footnote here. Remember Popper from our previous lecture for this. One thing that comes up in the lab session, and something that we also talk about in the tutorials, is different ways of measuring things. And I thought to show you this little schematic to maybe clarify what we're talking about here. So we have these four types that we can distinguish: nominal, ordinal, interval, and ratio. In some ways, these refer to the degree of precision that we have, as it says on the visual here. However, I'd really like you to think about these as different ways of measuring certain things. So it's important to keep in mind that this does not refer to what we are measuring. So is it age or income or some length of a certain object? But instead it is how we are measuring it. And I'll show you an example on the next slide what that means. But first, let me just briefly explain what nominal, ordinal, interval, and ratio are in the first place. So it starts with data or data, depending on where you're from. And this can take a variety of forms. Let's assume for now that all of these things are recorded in terms of numbers. There's numbers that represent certain values in the data. And that applies to nominal, ordinal, interval, and ratio. The way that we use those numbers differs a bit though. Let's start with nominal. Nominal just means we can measure a thing and we only measure different categories of it without necessarily looking at, are these different categories in a certain specific ordering? Are they at an equal distance to one another? Nothing like that. It's just different things. So for example, gender might be one of those things. Is someone cisgender? Are they not cisgender? Or are they just simply male, female? Just two categories. If it's sex, for example, these are just different categories. They are not in a specific order. When we code that data, however, we will give them a number. So we might say heterosexuals are value. We'll code those as value 0. Then bisexuals will code them as value 1, homosexuals will code them as value 2, etc., etc. And does this not imply an order to these categories? It just needs to have a unique number that is associated with it. And this is the way that we might record that in data. In sum, nominal is just categories and nothing else. Then one step up within the branch of categorical here would be ordinal. Ordinal refers to also just categories, and also not necessarily in exact distances from one another, but they are in an order as the name implies. So think, for example, levels of education. So we have primary school, secondary school, and tertiary education, like universities. These are not at exact distances from one another, but they are in some order. It's at least more education or longer education or more complex education. And so we can put them in some order. The way that we would code this as data would also be in numbers again. And so, for example, we might say primary is represented by the number 1, secondary is represented by the number 2, and tertiary is represented by the number 3. However, number 3 does not mean that it is exactly 3 times as much education as primary education. So we can really calculate with these values. We can say that these are exact numbers that we can do math on directly, but they do represent a certain order. This also means that if you are recording this type of information, that the numbers that we do attach to different categories, either nominal or ordinal, they are in principle arbitrary. So for example, for nominal, if we asked you what's your favorite food, and we say pizza, lasagna, or macaroni, different categories in no particular order, we could give them value 1 and 2 and 3, but we can also give them value 12, 37, and 102, as long as they are different. For ordinal, the same applies, except that they need to be in an order, the numbers too. So if we have, again, primary, secondary, tertiary education, we could give that value 10, 12, and 115. They are in an order, and they are in an increasing order, but again, the number itself is not a mathematical, useful number. Okay, so we call both nominal and ordinal categorical for this reason. They only represent categories. The other main branch is called quantifiable here. You might think of this as numerical, but that might be confusing considering we use numbers to write all of this stuff down. So let's stick with quantifiable. Quantifiable can be taken apart into interval and ratio. For both of these things, SPSS and many other programs will call these scale measurements, just to indicate that they follow an exact scale. In fact, SPSS will show you a little icon of a ruler with centimeters, for example, or inches if you're American. And if you think of a ruler, we can see that every centimeter is exactly the same length, and that means that we can do math operations on these, and they are meaningful. So 10 centimeters is twice as long as 5 centimeters. If it takes you 20 minutes to get to UCM in the morning, and your friend takes 40 minutes, it takes them twice as long exactly. So these are exact numbers, and they are an equal distance to one another. This applies to both interval and ratio, so there's no difference in that regard between the two. Where they are different is just that ratio has an absolute 0 point that makes sense in the context of the scale. So let me illustrate this by an example. Let's say that we are measuring how old someone is. We could ask them, what's your age in terms of a number, or we could ask them, what's your year of birth. Year of birth would be interval, because every year, the way that we count them at least, every year is the same as any other year. They are the exact same length. I'm not talking about gap years here. That's kind of irrelevant to the story. So disregard the idea of gap years for the moment. Every year is a year. However, we do have a 0 value when it comes to year of birth. Historically, people were born in what we now would call the year 0, but there were also people born before 0. Where we put that 0 in when it comes to year of birth is arbitrary. It's not a real absolute 0. When we ask people how old are you in terms of number of years, that it does have an absolute 0. We cannot have negative, we cannot be minus 5 years old, for example. And so everyone is at least 0 years old, and that's an absolute 0 value that we cannot go below. So that would be ratio. Another little example, maybe if that helps, would be to think of temperature scales. Most of you will have learned about different ways of measuring temperature in high school. And so most of us will use Celsius. Again, the Americans might use Fahrenheit. Both Celsius and Fahrenheit are interval measurements of how hot it is outside, because every degree in that scale is the same as any other degree in that scale. So we can kind of calculate with that. It's not exactly true that 20 degrees Celsius is twice as hot in all definitions as 10 degrees Celsius, but let's not get into that whole discussion. That's for a physics class. Contrast Celsius and Fahrenheit to degrees Kelvin. So if you remember from high school, degrees Kelvin is often used in science to indicate how hot a certain thing is, or how hot it is outside, or whatever. And 0 degrees Kelvin is also the absolute 0 possible. So it cannot be colder, there cannot be less energy in an object than 0 degrees Kelvin, because this is the moment where all of the molecules stop moving at all. So that's just an absolute 0 point. Again, so this would be ratio. Okay, enough about this slide. Let's move on. And just to drive it home a bit, here's an example of what different measurement types might look like in surveys. And this is important to realize when you're actually using this stuff in, for example, the project period or for a project in the future. Because at the moment of designing your survey, you're already deciding what kind of measurement type you will have in your data, which then will have a big impact on what you can actually do in terms of analyses. And we'll get back to that later on. So a typical approach that we might see, and I see this a lot in student projects, and generally, by the way, I would not advise this for most situations, is something like this. So we wanted to know how old someone is, and we asked them, are you between 20 and 24? Are you between 25 and 29? Are you 30 to 34? And then there's a category missing, I see, but you get the idea. So these are categories. So if you're paying attention, you would have noticed this is ordinal, right? So this is categories in an order. They are not exact, because if someone chooses the third category, 30 to 34, we can't really know if this person is exactly 3 times as old as someone who chose the first category, 20 to 24. It's just different categories in an order. A better alternative usually would be a very simple question, which is just please state your age, and you get a number and you get a year, right? So this would be a ratio measurement. Alternatively, and equally precise in this case, would be please state your date of birth, and we get a day. So if you want a day instead of a year, I guess this would be more precise. But essentially you get the year of birth here, and that translates exactly the same. But this would be interval. So this was the quick review, and I talked a bit more about these ways of measuring things, so that we can work on that. And the next thing that I want to talk about is measures of association. It sounds weird to put it like this. It's just calculations that we can use to see whether 2 variables, 2 things that we can measure, have a relationship to one another. not necessarily even whether they impact on one another, whether they have a causal relationship, although often that is kind of assumed, but just simply, do they go together? Do they have a relationship? We talked about Pearson's R, and so that's also where we will start. We call that correlation, and then when people talk about correlation, the word correlation, usually what they mean is Pearson's R. To be exact, Pearson's R coefficient, and it looks like this. You've seen this before, and you've used the M&Ms to actually visualize this. The lab session also has you do these things and produce them in SPSS. But to recap very quickly, Pearson's R is expressed in a value between -1 and +1, where either -1 and 1 exactly will be a perfect correlation. In other words, if we know the value of the x variable, we will know the exact value of the y variable. It's a perfect correlation, and we don't see that very often, right? When we do see it, it tends to be a mistake, but it depends on the field a bit, whether we would expect to see this. Absolutely no relationship between two variables is the value 0. Of course, you can see this in this cloud that has no particular direction. And then anything in between is some degree of correlation. This is not to be confused with the slope in regression analysis. This is a different thing. The slope, as in how steep is this line, how steep is this cloud looking, that is a different metric from the Pearson's R. You could think of the Pearson's R coefficient in some way as, if you imagine a Venn diagram with two overlapping circles, how much do the circles overlap exactly? Yeah? However, Pearson's R only works for scale variables, so interval or ratio, and it works also best for, or it only works for variables that are linear. They have a linear relationship. I'll talk more about what that means, linear relationship, in a couple of slides. But first, I want to tell you something about what we should use in other situations. So, considering that Pearson's R can only be used for interval and ratio variables, what if we have a nominal variable? Say we want to know if people who like pizza over lasagna also tend to have goldfish instead of sheep as pets, right? A weird example, I know, but I'm sticking to it. In that scenario, we would not use Pearson's R because, as we've established, that doesn't work here. It's for interval or scale, interval or ratio, in other words, scale variables, not for nominal variables. For nominal variables, we have other things. Historically, one of the earlier ones would be the chi-square, as you see here. I want you to kind of assume the names that I'm giving you. So it's called chi-square. Let's not get into why it's called that. Not this one, but most of the others that I will be showing you are named after a person. So that's just what they are called. I know that can be confusing. In any case, the chi-square is one of the older ones. It works, so it tells you something about, is there a relationship, yes or no, between two variables. We can get some idea about the strength of the relationship. It says here there's no indication of the strength of the relationship. There is, but it's hard to establish. A solution for this would be a later addition to this, Kramer's V. Again, Kramer or Kramer, I don't know, is the person who came up with this, and V is the letter he gave to it. And this starts to look more like something that we can use on multiple variables. Essentially, Kramer's V is a standardized version of chi-square, for those who want to know. Kramer's V ranges from 0 to 1. The way that we read that is not exactly the same as with the Pearson's R. There's different rules of thumb, and I've put them here on the screen for you, where a value of between 0 and 0.1 would be considered very weak, and then all the way up to 0.45, so not 1 exact necessarily. Everything over 0.45 would be considered a very strong relationship between two nominal variables. So that was nominal variables. What if we had ordinal variables? We wouldn't use Kramer's V, we wouldn't use chi-square, we wouldn't use Pearson's R. What would we use? Well, we have a couple of options. One would be Kendall's rank correlation, tau, which falls apart into two different types, tau B for square tables and tau C for rectangular tables. On the next slides, I'll just show you what a square on a rectangular table is. But in both cases, it ranges from -1 to +1. fairly similar in its interpretation to Pearson's R. It's not that far off. And we also have Spearman's rank correlation, or rho, as it is called. So I promised you I would come back to the square, and the rectangular association table is nothing else than just a square association table has as many categories on one variable and as it has on the other. So in this case, we have extreme left to extreme right with 5 categories: extreme left, left, center, right, extreme right, that's 5. And on income, we have very low income, median income, high income, very high income, also 5. So it's a 5 by 5 that is symmetrical, therefore square. Here's a rectangular association table where it's not the same numbers, a number of categories. Finally, we're coming back to the interval ratio measures of association. So as you know, we've already established Pearson's R, which is perfectly fine to use. But like I said, it assumes a linear relationship between 2 variables. I'll get back to linear and other requirements that we might have in the next slides. So only for interval ratio variables. It assumes homoscedasticity, another thing that I'll show you in the next slides. And like I said, assumes linear relationship. The advantage of a Pearson's R is that it gives you an exact coefficient at some point. And one alternative that we might have for interval and ratio is again the Spearman's rank correlation. So you're right, you saw this before on the previous slide. We can use Spearman's rank correlation for either ordinal variables, but also for interval or ratio, in other words, scale variables. The difference between Pearson's R and Spearman's rank correlation, as in when would you use which one of those two, is mainly that Pearson's R, like we've established, assumes a linear relationship and assumes homoscedasticity, which again I'll explain in the next slide, where Spearman's rank correlation does not. Spearman's rank correlation is more flexible in this way. The reason for this is that where Pearson's R has a certain calculation to basically look at the scatter plots idea. So imagine the scatter plot when you think of Pearson's R. It tries to draw a line and minimize the distances. But Spearman's rank correlation works differently. So if you imagine these tables that I showed you on the previous slide, for simplicity's sake, let's say we have a 2 by 2 table where someone has a low income and a high income and is left wing or right wing politically. If we sampled 100 people at random, we would expect, based on random chance, and the null hypothesis is true and all that, we would expect 100 people to fall into exactly 4 cells, each cell containing 25 observations. So that's the expected count in the cell based on the null hypothesis, so no relationship. And what Spearman's rank correlation does is it looks per cell at what is the number of people or number of observations that we would expect based on random chance. So with a sample of 100 and 4 cells to divide it 25. And what is what we actually see? So what is the observed cell count? So perhaps that's 30 in 2 of the cells and then 10 in 2 of the others. Wait, no, 20 in 2 of the others. And so that makes it more flexible because that means that it can also deal with nonlinear relationship and also with heteroscedastic, as that's called, distributions. I thought it would be easier to just show you that in a little graphic rather than try to explain it in words. Because when you see it, I think it's pretty easy to grasp. So what you see here is two different scatter plots with an x-axis and a y-axis, x on the horizontal, y on the vertical. And where on the left it's the relationship is homoscedastic. There's homoscedasticity, a difficult word. And you can see what's happening here. So if we were to draw a line through these dots here, it would kind of go up from the bottom left to the top right. And most of these dots on average will be a similar distance away from this line that we're drawing across the range of the x-axis and the y-axis. On the right-hand side, there's a heteroscedastic relationship where you can clearly see the distance of those dots to this hypothetical line that we're drawing increasing over x and over y. So as we go higher on x, more to the right, there's a bigger diversity amongst observations, in other words. So that's a heteroscedastic relationship, which Pearson's R cannot deal with, but Spearman's rank correlation can. Then, to follow up on this, we have linear as an assumption for Pearson's R, also for the linear regression analysis that we'll be doing, by the way, and that we have been doing. What does linear mean? I think most of you will know. On the left-hand side, we have a linear relationship between two variables. And if we were to draw a line through it, it just follows that line in terms of the pattern. On the right-hand side, we have a nonlinear relationship where obviously there's no straight line that we can draw through this. In fact, if we were to draw a straight line, it would just follow the zero there. And that would suggest no relationship. So in more concrete terms, Pearson's R on the left-hand side would do a great job. On the right-hand side, it would say there's no correlation, whereas clearly there is a pattern. And Spearman's rank correlation would be able to tease this out, and Pearson's R would not. So you might ask yourself, why shouldn't I just always use a Spearman's rank correlation then, if it's so flexible compared to Pearson's R? A very good question. In some fields, they will do this more than in others. However, Pearson's R is still one of the most used and most easy to communicate metrics that people will use. So if you can help it, that's still something that people will tend to prefer. Another thing to consider here, and this is basically also checking your data without just relying on the numbers alone, also just looking at what it looks like, is a note here on outliers. So outliers are observations, be they people or other things that you might be observing, that are outside of the rest of your data. This can be multiple observations, but in the example here, it's just one. On the left-hand side, you see an outlier that is called online, not online as in on the internet, but on the line that we are drawing. So if we imagine a straight line going from the bottom left to the top right, it's still on the line that we would draw based on the rest of the observations in the bottom left. And so what would happen in for Pearson's R, for example, is that the strength of the relationship is exaggerated. It's overestimated just because this one person or thing at the top there is kind of emphasizing that result, if that makes sense. On the right-hand side, we have what's called an offline outlier, and so that's off the line, outside of the rest of the data. And if we were to draw a line here, and so Pearson's R is kind of what Pearson's R is doing, it would actually underestimate the strength of the relationship for the rest of the thing, because it would, this one observation that is offline would kind of pull that line towards it, unreasonably so, because it's just the one thing. Of course, these can have different reasons. These can be actual, real, and valid data. It's possible, but in many cases, especially if it's so extreme as in these examples, it tends to point to an error in data collection or in measurement or these sorts of issues. So it may be necessary to remove these observations. A little note here, we didn't really have a chance to include this in the lab session right now, but we will have a follow-up on this in research methods too, where you can choose to work more on this. And I would recommend to look into it in research methods too when you have the chance, if you think that you might use these sorts of approaches, because a lot of students end up actually using this type of analysis as well, in addition to the ones that we're also discussing in their project period. It depends by field whether people use this a lot. So what if we wanted to compare the means between two different or more than two different groups of things? And there's two main procedures that we can use. We can use a t-test and an ANOVA. Both are fairly basic statistical analyses. And the way to see them is this is not similar to a Pearson's R in that it doesn't really look at the relationship between two variables per se. It's also different from regression analysis in that sense. It's just another technique that you can use, and you use it specifically to compare groups. So one classic example, of course, would be when you have an experimental setup and you give a stimulus to one group and a control to another group, and you compare whether they score differently on some dependent variable that you're interested in. You use a t-test for just comparing two means and an ANOVA for comparing multiple ones. Your coordinators or the methods lab will have more resources for you if you want to look into this further. But for now, I'm going to leave it at this. Instead, we want to move on to multiple regression. A multiple regression is nothing more than just the regression that we are familiar with, just adding more variables to the model. Which kinds of variables? Well, independent variables for now. And we're still focusing on linear regression. This graphic that you see is an attempt at a visual representation of what that might look like when we have three variables that we're comparing. Because I've showed you the scalar plots until now, which is basically two variables, in other words, two dimensions of your data. But it can also just show you the values of two variables, the x and the y. This is a three-dimensional graph that shows you three dimensions. It's about cars. I don't know anything about cars, but it's miles per gallon, as in how efficient is the car, is the weight of the car, and it's the horsepower, how strong the car pulls things, and the relationship between those things. And so what we're doing with multiple regression analysis, if it's three variables, is instead of trying to predict a line through it, y equals a plus b times x, if you recall, is try to predict a plane in this case. Right, so a flat surface in three dimensions. We can add more variables to this, and if you recall, you've seen this a couple of times before already in the course. For example, the support for radical left ideologies, they had a whole page with independent variables to explain a certain dependent variable. That would be tricky, of course, to visualize in this way. So we can only see in three dimensions, so this is still doable, but more than this becomes difficult to represent visually, but I hope this illustrates the point. Regression analysis comes with its own set of assumptions, like Pearson's R, and we are focusing on linear regression for now. There are other types of regression out there, and you'll find them at some point in the future if you pursue statistics further in the statistics courses, for example. But we're focusing on linear regression just because it's a good point to start with, and it is actually used quite a bit still. So obviously, one assumption that linear regression has is that relationships are linear. We talked about what linear means, so I hope that was clear. It also assumes homoscedasticity. We also talked about that, right? So where the distance between the observations along the line stay more or less the same. And it assumes interval or ratio data, in other words, scale data. But as you see in the lab session, we can cheat on that a little bit sometimes, depending on your field. I'm not advocating this necessarily, but this is where we can have a discussion about whether we think that's valid or not. It depends on whether we think certain variables are in fact measured as a scale or as an ordinal variable. For example, this could apply to political orientation. If we ask people in a survey on a scale of 1 to 10, how right-wing would you rate yourself? Do people read this as a scale that is exact, as in if they rate themselves 10, are they twice as right-wing as someone who scores themselves 5? Or are these really just categories of right-wingness? Again, this is open for debate, and depending on your assumption about how that is measured, you may or may not use it in regression analysis. So how is regression analysis different from correlation? Correlation is often used as a first step before people do regression analysis in a paper, but not necessarily so. There's papers or books that just use correlation, and there's also papers and books that just use regression analysis, and of course other techniques that are out there that we're not discussing at the moment. But they are different in some key ways. They are part of the same family, but they are kind of different in some key ways. Firstly, correlation does not assume causation, as you've heard before, most likely. Regression analysis does assume this. This does not necessarily mean that when you find a relationship in your data and you find it statistically significant, that therefore it is true in the real world for sure. It could also be that you're doing something weird with your model, but in general, regression analysis does assume a causal relationship. And another thing that we can do with regression analysis is that we can achieve a formula We talked about y equals a plus b times x, so the first part of the formula that you see here. And all we're doing now is basically adding more terms to it that are also, say, b times x and b times x plus b times x plus b times x. And there is a plus b times x for every independent variable that we are adding. All right, so the x's all refer to the scores on that particular variable, and the b's all refer to the slopes that are associated with that particular variable. In other words, how much they contribute to explaining the dependent variable, in other words, our y here. So we achieve a formula to predict a value on a dependent variable based on independent variables, plural. And so we're talking about multiple regression today. Here's another example. You saw the example with the 3D chart of cars earlier on when I started this part. Here's another way of representing it. So you can see where these crosses are. There's a scatter plot basically between a diet score, whatever that may be. I guess how much people eat or something, and their BMI, which we also look at in the lab session, BMI. If we just had the crosses there, we do a Pearson's R, we might not see any correlation. Maybe it would be a correlation close to 0, considering it doesn't really have a clear direction. However, when we do regression analysis, we can account for more variables. We can account for gender, there's males and females, and we can account for age. There's age over 20 and there's age lower than or equal to 20. And the key thing is that we can draw a line for each one of those groups. So essentially you see 4 lines being drawn here. And then when we draw those 4 lines, we clearly do see a pattern between diet score and the BMI that these people have. But it just depends on how old they are and which gender they are. So why would you do this? One is you might have a better theoretical model. So it's possible that you found some theory that someone is writing down in some sort of book or a paper that you're reading. I think, hey, that's interesting. Let's see if it actually holds up to empirical scrutiny, into data that we gather. And sometimes these theories get complex, and you want to account for multiple dimensions, multiple aspects that they include in the theory. And so, for example, here, if you had a theory about diet impacting on BMI, the theory might also say, well, this depends on the gender and the sex in this case, and the age as well. In this case, you need a better theoretical, empirical model also. And it can also just be a better empirical model as such. Perhaps you don't really have a full-fledged theory about a certain thing, but you want to explain things better, or you want to explain more of the diversity that we have on the y variable, on the dependent variable. And that's basically what I was saying here before, when we had just the crosses between diet score and BMI without sex and age, we would see no relationship, and that's not a very good empirical model. It suggests that there is no relationship between diet and BMI, but there is. It just depends also on age and sex. And finally, we could have control variables in our regression analysis. And control variables, I'll talk about that. I have talked about that in the previous lecture about this. They are just variables that are not your main interest. So in this case, it might not be that you're interested per se in sex and BMI, but you need to control for them, you need to take them into account to even see a relationship between diet and BMI. Something to be aware of, this procedure, multiple regression analysis, is always reliable, as all of the other procedures are that we are doing, especially when you do them in a computer program like SPSS, because the program always does the same thing. It's just a calculator in a way, and a calculator is predictable. It does the same thing, so it's reliable. However, what you're doing is not always valid. It can be stupid, right? You can have a weird model. You might even find statistically significant results based on your weird model. That doesn't necessarily make it valid. We'll talk more about validity and reliability in a bit, by the way. First, let's talk a bit about some special variables in a multiple regression analysis. The first one is dummy variables. And dummy variables are very simple variables. And they answer the question, what if we want to include nominal variables in our regression analysis? Like I said, one of the assumptions for regression analysis is that it works on scale variables. So what if we wanted to account for example, nationality, right? So we have some Dutch UCM students, some English, some Italian, some French, so to speak. And we have given them different numbers in our data, but we can't really include them in the regression analysis, because regression analysis will then assume that it's a scale variable, and it will say the higher value is a higher score on nationality. That doesn't really make sense, because they are not higher, they're just different. And the way to deal with this is dummy variables. So how do they work? They either have as value 0 or they have value 1, which means it's either false or it's true. And so what we do basically is, when we have a variable that measures, a nominal variable that measures nationality, for example, we might say 1 is Dutch, 2 is German, 3 is French. What we do then is we split that one variable up into 3 separate variables that measure, is this person Dutch, yes or no, 1 or 0, is this person German, yes or no, 1 or 0, or is this person French, 1 or 0. And those are mutually exclusive. So in the example, there's no multiple nationalities in this particular example. And so when we have that, essentially what we have is we have a variable that measures the degree to which someone is a certain nationality. So is this person, how much is this person Dutch? And then the only possible values are 0% or 100%, so to speak, right? So that is technically a scale variable. It's just that we don't really have any variables, values in between. It's just a 0 or 1, but it is scale. So it's kind of cheating the system a bit, but it does work, and it is a valid way of doing it. Something to keep in mind, and we'll look at this in the tutorial a bit, is that these dummy variables need to have a reference category. This means that there's one of these categories that we are comparing the other categories to. In the actual application, this is something that you can choose to do in research methods too. In the actual application, that we'll leave one out of the regression analysis, and that becomes our reference category. But in the tables that you'll see in the tutorials, it is just simply mentioned as the reference category, and that means that we, for example, in Dutch, German, French here, we would not have a value for Dutch, and the value that we get for German is actually the value how Germans are different from Dutch as compared to Dutch. The value that we get from French is also how the French are different as compared to the Dutch. This is how you read that. Again, we'll spend some time on this in the tutorial. A second type of special variables is called interaction effects. And these answer the question, what if the effect or the impact of one variable is dependent on another independent variable? So in other words, 2 or more variables together may have a particular effect beyond those 2 variables separately in and of themselves. A simple example, just to get the idea across, would be if you drink coffee and you want to sweeten it up, you need to do 2 things. You need to add sugar and you need to stir the coffee afterwards. If you do either one of those things separately, the coffee won't get as much sweeter. So if you add sugar, perhaps something will stick and it will become a little sweeter, but for the most part, the sugar just sits at the bottom and the coffee is still as bitter. You need to also do the stirring, but if you do just stirring without adding sugar, of course the coffee doesn't change at all. You need to do both those things, and how much sugar you add and how much you stir afterwards, the interaction between those 2 actions, that determines the sweetness of the coffee. That's kind of the analogy that you can think of, and this applies to a whole lot of things. For example, asbestos that was used as a construction material in the past and is now kind of being taken out of homes in many countries, was found to be a carcinogen, so that it caused cancer in and of itself as well. And of course, as we all know, smoking causes cancer too. However, when people were exposed to asbestos and they smoked, their risk of cancer was multiplied, not more than just the 2 separate effects. So this is an example from research where there is an interaction effect. The final section that I want to talk to you about in this online lecture is some things about quality control. And we'll first talk about validity and reliability, two very important concepts. So I want to use the analogy of a shotgun shooting at a target here as to explain validity and reliability and what they are. So imagine that we're taking this target and we're shooting a shotgun, and the bullets that come out of it represent the measurements that we take. So in a survey, for example, that would be the survey questions. Here are some results that we might get when we shoot this shotgun. In the top left corner, you see an example of something that's both unreliable and unvalid. So this is not what we want, obviously. We missed the target and we are all over the place. So it's unreliable because it doesn't measure the same thing every time. In other words, the bullets are not in the same spot here. So an example in a survey would be that we ask a certain question in the survey, but different people answer it very differently, and they assume different things about what is meant in the question. So perhaps the question wasn't clear, for example. It's also not valid because we missed the bullseye in this example here. So we're not measuring what we say that we are measuring. A little example from social sciences in a survey could be, for example, using church attendance to measure someone's religiosity, how religious they are. Perhaps they go to church all of the time, but they don't really believe in any sort of God. Or perhaps they are very religious themselves, but they never go to church. So it's measuring a different thing. It's not valid. On the right to that, the top right, we have something that is unreliable, but kind of valid. So it's unreliable because it's all over the place. It measures a different kind of thing every time that we measure it. Every bullet is different, but it is overall valid. So as a whole, it kind of hits the bullseye. It is kind of around the thing that we want to measure, but it's just not very precise. Bottom left corner, we have something that's reliable but not valid. So it does the same thing over and over again. We do measure something consistently. It's just not the thing that we want to measure. So church attendance to measure religiosity could be a good example here as well. It's easy to measure and it's kind of reliable because we can just count how many people there are in a church. It's just not perhaps valid. It's not measuring the thing that we say that we're measuring, which is how religious people are. Of course, the thing that we want is in the bottom right corner where it's both reliable and valid. We hit the bullseye and we hit it consistently. You'll see in the literature that there's many different types of validity. They have names and all that. The book that we have referred you to also lists a whole bunch of them. Two important ones, though, that I'd like you to remember are face validity. In other words, does it measure what it appears to measure on face value? And the second one is construct validity. Does it measure the theoretical concept? So is it a good operationalization of the thing that we say that we are measuring? The next topic that I'd like to talk about is explained variance and related to that multicollinearity. I'll explain what that is in the next slide. First, explained variance. So imagine that that this circle represents the y variable, in other words, the dependent variable that we try to understand, that we try to explain, and we are adding some independent variables to do that. So for example, let's say that y represents someone's monthly income, and x1, the first variable that we use to explain it, might be their level of education. x2 might be the money that their parents have. Perhaps if their parents have more money than the person that we're investigating, the group of people that we're investigating also earn more money. And perhaps there's a third variable, which is whatever it could be, what sector of industry they might be in. So if they're in finance, they might make more money. If they're in philosophy, perhaps a little less. All of these things together, where they overlap the y circle, is what we call explained variance. So this is your whole model. In a multiple regression analysis, all three of these variables together exist in a single calculation. So it's y equals a plus b times x plus b times x plus b times x in this case. And altogether they explain a certain thing. It's explained variance. Something to keep in mind, however, is that these things overlap. This is not necessarily an issue. This is always the case. For example, here we looked at, what was that? The level of education and what sector of industry they are in. Those things might be correlated amongst each other, just the two of them, x1 and x3. And so they share also some variance that they explain in the y variable. The calculations that SPSS and other computer programs use to calculate this can deal with some degree of this. And it's okay. So that's just a shared explanation of variance between of y between x1 and x3. And in this case also a bit of x2. However, this can become an issue if they overlap too much. So for example, if the sector that people work in correlates very, very strongly with their level of education, so perhaps we have a specific slice of the population, then this explained variance is overlapping quite a bit. Okay, so where it's still green overlapping red and where it's still purple overlapping red and without overlapping anything else, those are very slim slices here. And this might actually cause an issue, which is called multicollinearity. And multicollinearity will cause your analyses to become unpredictable and unstable. So how you will see this, the first thing that you'll see often is when you change a little thing in your model, all of the effects suddenly completely change. And this is sort of a giveaway that you should check into multicollinearity. And so how would you do that then? How do you check for multicollinearity? The literature that we've given you actually has sort of an instruction on how you might do this. You don't have to do this all of the time for projects in a class or something, but keep it in mind for the more serious stuff that you want to do in the future, or when you think that you see this issue happening. There are definitely ways to check for it, and then now you know the word that you should look for in the literature to figure out what are some of the things that you should report on then. In SPSS anyway, there is a function called collinearity diagnostics. And here are some rules of thumb. If you just want to check that out very quickly, you can run those collinearity diagnostics. It gives you a bunch of numbers, of course, as most of these procedures do. And the rules of thumb are that the tolerance is over 0.4 and the VIF is below 10. Again, check the literature that we provide you if you really want to go deeper into this. If not, just remember that is there. Multicollinearity is, by the way, not something that I will ask you about on the exam, because we don't really have time to go deep into it. And as always with statistics lectures, I'll end with some silly pictures. So this is your reward. Enjoy it. Thank you for watching this lecture, and have fun in the tutorials. I'm looking forward to see you all there. And see you next time.